And rolling. Okay, this might be the last time that I go through this whole rigmarole at the beginning, but just in case this is the first one of these lectures that you're watching, let me explain some stuff. If you look, I can never get this figured out. Okay, here it is. If you look down there in the course description, one thing you're going to see is a link to the guided notes. And that's what this is. It's the guided notes. It looks rather blank, right? Well, that's because I'm about to fill this all in. I'm going to actually give you a nice little lecture and fill this all in. This one's 5 pages. It's not, it was 2 pages. I'm just making it bigger to give me lots of room to write. So it shouldn't be that bad. But anyway, you also have a link. If you continue to look down there, there's right next to that, there's a homework link, right? So this is what you're printing out. This is what you're handing in the Dropbox, which is in D2L, and this is 4 pages of stuff too. Cool. So a little bit of practice finding areas and volumes. That's what we're heading into here. It's actually a important thing, like in some well, like civil engineers sometimes have to figure out how much concrete they need and so on. So area volume, it's important. Let's go on here then, huh? Turn these off. There I am. Let's start. So, first thing I got to do for the first few pages is basically give you some formulas. And I don't want to just give you formulas. I want to talk a little bit about properties of these various shapes that we're going to look at. And by the way, let's turn me off because you're not going to see much anyway because I'm going to have my head way over there. Okay. Hey, we're going to talk about some other properties. Some of this you're going to know, some of this maybe you don't know. But let's start with equilateral triangles. Remember what equilateral means. Equa means equal, lateral means side, equilateral means equal sides. I suppose there's no reason you couldn't call it an equiangular triangle because all the angles are equal too. By the way, all of these angles are 360 degrees. What'd I just say? All of these angles are 60 degrees because you know that there's 180 degrees in a triangle. So if there's 3 equal angles, 180 divided by 3, they must all be 60 degrees. Here's our main concern for today. What's the area of that thing? Well, each side has a certain length. We'll just call it little a, and of course being equilateral, they're all the same. And if you want to find the area of this triangle, you're going to want to take one of these sides, a, and you're going to want to actually square it, multiply by the square root of 3, and divide by 4. Works every time. Okay, a squared, square root of 3 over 4. Now, where is this formula coming from? Anyway, it comes from basically, you might remember that for any triangle in the world, you can use this formula, 1/2 times the base times the height. And so if and the base and the height have to be perpendicular, so that's why I'm cutting this thing in half. I'm trying to make a nice right angle over here so that I can use 1/2 base height using this as the base, this is the base, and this is the height. So, okay. Now, if this is a all the way across, then actually the base must be a over 2. So I can use a 1/2. I can multiply by side a and over 2. And then how am I supposed to get this height here? Well, you could always use Pythagorean theorem, right? H squared plus a over 2 squared has to equal a squared. You see what I did there? I did the old leg squared plus leg squared equals hypotenuse squared. Now, if I solve this thing for h, what am I going to get? Well, let's see now here. That's an h squared. That would be an a squared over 4. This would be an a squared. Now, if you were to subtract this on both sides, basically you've got a 1 a squared, which is the same thing as 4/4 a squared, and then I'm subtracting the a squared over the 4, which is the same as 1/4 a squared, and you're getting 3/4 a squared. H squared is equal to 3/4 a squared. If you take the square root of both sides, you get the square root of 3. Square root of a squared is a, square root of 4 is 2. And that's why we're getting that the height is square root of 3 times a over 2. Okay, so who knows, you might want to actually jot that in here. That could be useful. I think I'll write it this way though. A square root of 3 is the height of this triangle coming through the middle. But anyway, continuing with our area formula, we've got various things happening. You'll see that we've got an a times an a is an a squared. We got a square root of 3. And then we've got a 2 times a 2 times a 2 is an 8, right? And then you say, we're supposed to get a 4. Yeah, I know. But remember, that was only for this side. We have two sides. So if you want to double that, I suppose I should have done that in the first place, really. So I'll call this a of half the triangle. So 2 times that answer is what we need to do. 2 times a squared square root of 3 over 8, which is where we get this formula, a squared square root of 3 over 2 cancels into the 8 4 times. Okay, now here's what I really like about doing this on my iPad. I can erase all this. Hopefully you wrote it down a little more neatly if you actually want it. Actually, you know what? Maybe I can do it this way. I'm on a learning curve here. Don't you fret none. I'll be getting pretty good at this iPad thing pretty soon. There's the key information that we need for equilateral triangles. Now, what about all other triangles on the planet or in the universe? Let's be inclusive here. The entire universe. So I'm just going to draw a weird looking triangle. See, it's a little inconvenient to use area equals half times the base times the height. You could, I might as well write that formula here. This always works. 1/2 times the base times the height always works. It's just that you got to be careful what you mean by a height. A height is straight up from the table. Straight up from the table. So if you wanted to find the area of this triangle using that formula, you could call this side the base from here to here. Call that the base. But the height would have to be over here. So it wouldn't do you much good if you knew like what this side was or what this side was, because you need the height in order to figure out this area. Or you might remember from not so long ago, I talked about my very favorite area formula for triangles. 1/2 AB times the sine of theta. Remember this one? The nice thing is that A and B can be any two sides. I was going to say two adjacent sides, but no matter which two sides you choose, they're going to be adjacent, right? So those are two sides, and then this is the angle between them. Between the two sides, okay? It has to be between the two sides. So if I called this A, let's just say, I called this A, that's my side B, so I want to put the A and the B into my formula here. That's nice, but the theta that I have to use would have to be here. It has to be that angle. Let's make that look a little nicer. It has to be that angle there. If somebody tells you what this angle is, it's not doing you any good. If somebody tells you what this angle is, it's not doing you any good. Not immediately anyway. You'd have to figure out what this angle is in order to use that formula. So that's very important to keep in mind. You know, formulas, you got to be careful how you plug into formulas. You can't just stick anything in there. It's like, you know, you're making a smoothie. You're going to put stuff in the blender. Are you just going to put anything in there? No, you're not. You got to choose carefully, right? You got to go by the recipe. So the formula here has got a, it's got a recipe, side, side, and the sine of the angle that's in between those two sides. Okay, so I hope I made that point clear. Those are the two main area formula, and we've used them before, so I don't think I have to say too much about them. And then don't forget there's that other one, that freaky formula called Hero's formula. I'd still love to know what this guy was thinking. Or, you know, how did he happen to run across this formula? I have no idea. But the formula goes like this. A is a big giant square root. You're taking something called the semi-perimeter. You're multiplying it by S minus side A, S minus side B, S minus side C. Remember, S is semi-perimeter. That's what it stands for. And I suppose I could write the formula for semi-perimeter, but what does it mean? Well, the perimeter is what you get when you add all three sides together. And the semi-perimeter means cut it in half. So if you use the semi-perimeter, you can use this Heroes formula. That's going to be helpful if you happen to know the three sides. If you know what the sides are, then you might as well use this formula. If you only know like two of the sides and one of the angles or something, then you're probably going to want to use this formula. Or if you're like really lucky and you happen to know the actual perpendicular height, then you could use that formula. All angles add to 180. I think that's enough about triangles for now. Quadrilaterals. So that would be 4 sides. Things with 4 sides. Rectangle. Everyone's favorite, right? So just pretend I'm drawing a perfect rectangle. Boy, that's like not at all perfect. I'm going to try just a little bit better than that. Okay, trying to draw something that would convince the average person it were a rectangle. So that's a rectangle. The area, I think you know this. It's basically, you could say length times height, width times height. I'm going to say width times height, where one of these sides is the width and perpendicular to that is the height. These are all right angles. Everything's at 90, 90, 90, 90. So that's kind of nice. All angles are 90. Opposite sides are parallel, right? So this side's parallel to this side, and this side's parallel to this side. What else could we say? We could say the opposite sides are equal. So again, this side's equal to this side, and this side's equal to this side. Not just parallel, but actually equal length. And here's another thing that might be kind of might come in handy someday. But if you were to draw the two diagonals, I think you can recognize, yeah, the diagonals have the same length too. But the diagonals bisect as well. In other words, they cut each other right in half. Okay. That's what I'll say about rectangles. Let's talk about parallelograms. Parallelograms look a lot like rectangles that got tipped over somehow, like they're leaning, like they're not long for this world or something, you know. So it's a rectangle that got sort of tilted over. Well, how the heck are you supposed to find the area of that thing? Well, the formula is actually near the same. Base times the height, where this is the base. But remember now, height has to be straight up from the table. That's the problem with this thing, right? So you have to look at the distance straight up from the table. That's the height. So if you want to get the area of this thing, you're going to have to figure out that height somehow. What else can we say about this? You could say that these angles that are opposite must be the same. These angles must be the same, right? What makes it a parallelogram is that this side's parallel to this side and this side's parallel to this side. Of course, they're equal lengths too, so I might as well leave those hatch marks there because this side is parallel to and the same length as this side. This side is parallel to and the same length as this side. What else can you say about parallelograms? Well, you know what? I could say, let's use a different color this time. I could say that if you were to draw these diagonals here, the diagonals do bisect. That could come in handy. The diagonals do bisect. That's supposed to say bisect. Let's make it say bisect. The diagonals do bisect. Again, when you're working around one of these diagrams trying to figure out various things, sometimes it's useful to have a couple of facts that you just happen to know. Rhombus. What's a rhombus? A rhombus is a parallelogram where all sides are equal. Sometimes if you turned it sideways, it might look like a diamond or something, but I'm trying to make it look like all of these sides are equal. It's not a square because it's crooked, but all of these sides are equal. That's a parallelogram. What's good about parallelogram? Well, if you want to find the area, I'm not going to give you a formula. You know why not? Because isn't it kind of the same as parallelogram over here? Sure it is. Use parallelogram formula. Or I suppose in some circumstances you might want to just kind of, if you think in terms of it's two equal triangles, well, it is two equal triangles. So if somehow it's easier, maybe you know this side, this angle, well, then it's going to be kind of nice to get the area of this side, right? Because remember, we had a nice area formula right here that'll work for you. Just saying. You know, you don't have to use the formulas they give you. Most of the time, you just kind of work your way through things using whatever kind of observations you've got there. So let me add this as an actual fact, though, to our repertoire, or whatever you want to call this, that these diagonals do bisect each other. So far, all these diagonals have been bisecting each other, but these diagonals bisect each other. And I can actually say a little bit more than this. The diagonals are 90 degrees to each other. That's a right angle, that's a right angle, that's a right angle, that's a right angle. They're all right angles. That's only true for a rhombus. Or I suppose a square as well. But the diagonals bisect. The diagonals are at 90 degrees. What else can we say? Oh, here's what we can say. See, I don't really know what this angle is, alpha. I'm going to call this side alpha. I think you can tell by symmetry that these are all the same angle. In fact, I should probably write that down. The diagonals bisect the angles there. That's not going to be true generally, but it is true for a rhombus. So when I'm saying that this angle is the same as this one, I'm actually correct. So I'm calling all of those alpha because they have to be the same, right? Just look at the symmetry of the darn thing. And then this angle, I don't know what it is, so I'll call it beta. So I have four angles that are all the same there, beta, 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 beta. And remember that this is a 90, which means that this is a right triangle, which means that the alpha and the beta must add up to 90. Because remember, for any for any right triangle, the two acute angles will add to 90. So you got a rhombus like this. Notice if somebody tells you what this angle is, you can cut it in half and say, well, that's what alpha is. And then from there, you can figure out what beta is right off the bat. So it's useful. It's useful information. So all I got to say about parallelograms, I think so. So let's talk about these trapezoids. You've probably seen trapezoids before. The thing that makes it a trapezoid is that one pair of sides is parallel. Of course, you're not going to have two adjacent sides be parallel. But one pair of opposite sides are going to be parallel. These sides can look whatever angle you want. They can do wherever they want. But you have one pair of parallel sides. If at least one pair of parallel sides, or I should say, if at least one pair of sides is parallel, then it turns out there's a little bit of a nice formula you can use to find its area. I'll call the length of that side A, I'll call the length of that side B, and to emphasize that H must be straight up from the table here. I'm going to draw it in a different color and off to the side. There's your height. And it turns out that the area of the trapezoid is, nifty formula, watch this, A plus B times H over 2. This formula has basically two parts to it. A plus B over 2 is the average of these two sides, right? So it's kind of like giving me, well, the average would be like the length going right through the middle, or the width going right through the mid-height here. Okay, that's what the A plus B over 2 is, times, of course, the height. That's how you might remember that formula. I think we're good with trapezoids. What else we got? Oh, we got some circular things going on here. New page. So I got to try to draw a circle. You gotta try really well. Try really hard to draw a nice circle. Whoa, I suppose there's nothing stopping me from grabbing a bottle cap. But that came out okay. So there's a center point here, and every point is equidistant from the center, right? That's how you define a circle. So the characteristic dimension here, you might say it's the radius, or you might say it's the diameter. Of course, the radius is exactly half the diameter. Diameter is exactly twice the radius, so it doesn't particularly matter whether you play with radius or diameter. I have a habit of playing with diameter. And so the formula is pi times d squared over 4. That's the formula for area. Now, if you were thinking, wait, isn't it pi r squared? It is pi r squared. But remember, radius is radius is not 2 times diameter. Radius is half the diameter. So the radius is the same as half the diameter, and if you work this out, you get pi d squared over 4. So pi d squared over 4 is the formula I'm going to use most often. And then the circumference of this thing, you could say 2 pi r, but 2r is the diameter, so you might as well just say pi times d. Pi times the diameter is the circumference. Notice the circumference is really just like a perimeter, right? It's like the distance around the circle. This formula is kind of interesting because think about the think about the d squared here. The d squared would be like the area of the square that this circle fits in, because it's got a length of d all the way from top to bottom. It's got a length of d all the way from side to side. So d squared by itself would be the area of that square. And so you've got this this multiplier here, pi over 4, which is something like 3/4, right? So it's kind of like saying that the area of this circle is about 3/4 of the area of that square. I just think that's kind of cool. Well, if you have one of those half circles, which means you cut it exactly in half, so you must have cut through the center of the circle, right? So there's the center right there. Well, guess what? The area is going to be not pi d squared over 4, but half of that. And if you take half of something, that basically means double the denominator, right? Because if you were to multiply this by 1/2, the 2 times the 4 would give you the 8. That's the area, and then we can get I guess you wouldn't call it a circumference, would you? Here's a kind of a funky perimeter formula. Now the perimeter means the distance all the way around this thing. And so you could say it's, well, you've got the diameter, that's part of your perimeter, and then you've got like half of a circle circumference. Half of a circle circumference plus the diameter. Now if you could put that together into a nifty formula that looks like this, d times 1 plus pi over 2. Kind of a cool looking formula, right? What you want to do with formulas, you want to chew on them a little bit and see if you can figure out where they came from, right? Because if you just look at the formula, you can say, ooh, formula, wow, weird. But notice if you multiply, if you distribute d times 1, you get d, and that's the length of this. And then if you were to multiply d times pi over 2, you'd get pi times d, and you're cutting it in half because you only got halfway around a circle, right? So that's where this formula is kind of coming from. Boom. All right, cool. There's not much else to say. Well, there is. There's a cool thing I'm going to say about these. There's something called Thales' theorem. I don't know if it's Thales or Thales. It's probably Thales, but it might be Thales. Somebody named Thales or Thales had a theorem, and it goes like this. You can draw a triangle starting at one end of your diameter and the other end of the diameter, and then any place you put this on the circle, that's going to be a 90 degrees. Doesn't matter where you did it. I could do it here. Well, then that would be 90 degrees, and so on. Any triangle that, the hypotenuse is going to be the diameter here. use this as your hypotenuse. Just connect to any point on the circle. You're going to have yourself a nice right triangle. So that's pretty cool. That may come in handy at some point. Sector. What's a sector? A sector is like a pizza slice. So a pizza slice would look something like this. Now it doesn't have to be a, exactly 1/8 of a pizza. It could be half of a pizza or a third of a pizza or whatever. But it's like a pizza slice shape. And there's gonna have to call that the radius, really. So the assumption is that this is where the center of the circle was. And then this angle here we're going to call theta. And I'm going to call it theta degrees. Okay, and that's worth highlighting. In fact, that's worth highlighting in a color that we can see real well. Degrees. I'm talking about degrees here. Theta degrees. So if you're talking about theta degrees, then here's what the area formula looks like. You take theta and you divide it by 360 times pi r squared. Ask yourself where the heck that formula comes from. Hint, pi r squared is the area of a full circle. So what's this then? This is what fraction of a circle we have, right? If I had, for example, let's say theta was 60 degrees, I would have 1/6 of a circle, right? 60 degrees, whoops, 60 degrees, oh boy. Trying to draw it so everything is 60 degrees. There we go, everybody 60 degrees. You got 1/6 of a circle. And so that's why you multiply by 60 over 360 is 1/6. So that theta over 360 is just the ratio of how much of a circle have I got here anyway. There. What about perimeter? Or perimeter. Wouldn't call it circumference, would you? Perimeter, let's look at this cool formula, see what you think of this one. R times 2 plus theta pi over 180. Let's see, where does this formula come from? Well, r times 2 is adding up this side plus this side. So that explains the r times 2. What about the r times this thing? Well, let me just kind of write that over here for reference. I'd be looking at a theta pi r over 180 degrees. What you can see here, pi times r, remember the circumference of a circle, the formula we used before was that the circumference is pi times diameter, which diameter is 2r, so it's pi times 2r is another way you could say it. That's an r. Or you could say 2 pi r. I guess I should have done that in the first place. So this this pi r has to do with this, right? Now usually we have a 2, but that's for a whole circle. We don't have a 2 over here because it's a half a circle. Wait a minute, is that what I want to say? 2 pi r. Oh, yeah, I know how to do this. Just bear with me here. Here we go. Come on, you. Okay, leave the 2 there for now. 2 pi r. Now, usually, if you wanted to say what fraction of a circle this is, just like we did it over here, we said theta over 360. That was the fraction of the circle, because we don't have a whole circle's worth of circumference. We just have a fraction of a circle. And so what's happening then is this 2 is canceling into the 360 to give me a 180. So that's where this 180 comes from. Okay, cool. So it's fun to look at these formulas and try to figure them out. So your notes hopefully will be neater than mine. Whoops, that's not what I want to do. Let's talk about a segment now. What's a segment? A segment is not quite a pizza slice. It's kind of a, well, it's, what are you doing? What are you doing? Okay, it looks kind of like this. Imagine taking a circle and sort of slicing just a little bit off of it like that. That's what we mean by a segment. Now the segment has properties. Let's see now. It came from a whole circle one day. So this has like a length of r. This has a length of r. This has an angle of so many degrees. So that's kind of your reference information over here. But we want to know, well, what's the area of this thing? What's the circumference of this thing? Well, the area goes like this. R squared over 2 theta pi over 180 minus the sine of theta. And I think I'll just give that to you for now. We will revisit this formula later. I'll have to revisit this when we look at radians. You need radians to get it. So just a note to self. That's not, I wouldn't turn the it into a pi. I didn't like that. That's not what I wanted to do. Okay. You need radians if you're going to understand that formula perfectly. But for now, let's just take it as a received wisdom. And let's get to the conics, which is definitely going to have to be received wisdom. Conics, there's two kinds of conics I want to look at. I want to look at a parabola, and I want to look at an ellipse. Now, a parabola, you can generate a parabola like if you did a graph with XY paper, right? You can just kind of say, well, when x is 0, y is 0, and when x is 1, y is 1, and when x is 2, y is 4. I'm going to assume you've seen these kinds of things before. If you want to make it a little more accurate, you could say when x is a half, y is a half squared, which is only a fourth. And when x is 1 1/2, you'll end up getting, like, my pencil tip's falling off here. You end up with a shape that looks something like that. Okay, so that's a parabola. Now let's not, the parabola of course climbs forever, but let's not worry about that so much. Let's just allow ourselves to stop there and define like this little rectangle here. So this side of the rectangle has length A, and this side of the rectangle has length B, and we're interested in basically what's this formula? Whoops. What's this formula? What's the formula for that area? What's the formula for that area? They both have to do with A and B. And this is just the coolest thing in the world, I think. Turns out that area 1 is, well, you take the rectangle, A times B, and you multiply it by 2/3. And area 2, you take the area of the rectangle, A times B times 1/3. Who'd have thunk it? So this parabola splits the rectangle into two pieces, where this piece is exactly 2/3 of the whole rectangle, and this piece is exactly 1/3 of the whole rectangle. That's just kind of cool, is what that is. So you have parabolic mirrors or parabolic hot dog cookers or whatever. That area formula could come in handy for you. The last thing we're going to look at is an ellipse. And the way you define an ellipse is if you had like x and y axes, the way you would generate an ellipse really is you would take two nails, put a nail there, put a nail there. These are called the focal points. You would then take a loop of string. So try to picture a loop of string that was, I don't know, let's say it went through there, right? So picture this as a loop of string. And you would pull this loop of string with your pencil all the way around, and you would end up generating an elliptical shape. So I'll just ask you to try to imagine that. What we really need to know for this lesson is that an ellipse basically is like kind of like a stretched circle, I guess is what you might call it. So try to picture that was a perfect ellipse. It's not a perfect ellipse. It's much too blunt on this side, but an ellipse. So the characteristic dimensions of this thing are that we're going to call this length A and this length A, and it's perfectly symmetrical, of course. This length B and this length B, perfectly symmetrical, of course. So what the heck's the area of this thing? What the heck's the perimeter of this thing? Well, the area is, and this is amazing to me, but it's pi AB. Let's think about that formula for a little bit. Pi times A times B. Well, if you had a rectangle, the full rectangle here, you'd have a side 2A one way, and you'd have a side 2B the other way, and so you get 4AB squared. And then you take about 3/4 of that, remember? So if you take about 3/4 of that, this is referring back to when we played with the area of the circle, and I was saying, yeah, it's about 3/4 of the containing square. Well, this is about 3/4 of the containing rectangle. Not really 3/4, it's actually pi fourths. And so if you multiply this, pi over 4 times the 4ab squared, the 4's cancel, and you get the, why am I squaring that? You get the pi ab. You don't square the b. Okay. Okay, there. That's all the area formulas and playing around with some nice shapes. This is cool. We're going to end with an actual example. And the point of this example is that often you have to use more than just one formula. Usually, often, you have to kind of break a problem into parts and say, well, I kind of see, you know what I kind of see? I kind of see like a half a circle here. And I kind of see like, you know, maybe a triangle over here. And maybe some kind of a rectangle over here. Or here's another way you might do it. You can say, I see a half a circle here, and I see like a trapezoid. We got formulas for trapezoids, right? So that's probably what I'm going to do, is break it into a semicircle and a trapezoid. Now, in order to do that, we're going to need to have some dimensions, right? Like, we're not going to be able to do anything with circle formulas unless we know how far across that is. And I don't know how far across that is, so I'm just going to label it a D for now. Somehow we're going to have to solve for that D. How can we solve for that D? Well, here's the information they gave us. We know how big this side is. I know D is shorter than that. How much shorter than that? Well, if I could figure out, look at this triangle over here, right? If I could figure out this side of the triangle, the bottom side, I could subtract it from 510, and I would have my D. So that's our first plan. So let me start doing that now. I'm going to basically do a dotted line down here. I dropped a perpendicular, so that's a nice right angle there. I'm going to call this little length here side A, or length A, and then I'm going to use SOHCAHTOA. I've got a right triangle, that's 55 degrees. I want this side, I have this side. So think back to your SOHCAHTOA stuff. Am I using a sine, cosine, or tangent here? If you said cosine, you'd be right. This is going to be a cosine thing. So remember ka, SOHCAHTOA. The cosine of an angle is the adjacent over the hypotenuse. That's definitely the hypotenuse. If I'm using this angle, that would be the opposite over there. So A would be the adjacent. And so the cosine of 55 degrees then is going to be A over 245 millimeters. Basically, you multiply both sides by 245. 245 times the cosine of 55. I gotta type this out here. 245 times cosine of 55 is, I'm getting 140.53. I'm going to use 5 sig figs here. 140.53, and this is millimeters. Cool. So that means that the diameter, maybe I'll use a different color here. The diameter would be this 510 minus the A would give me the diameter, right? So the diameter is going to be 510 millimeters, take away 140.53. It's going to be 369.47 millimeters. All right, let's start getting some area here, because that's what the problem asked for, is the area. So let's get some area here. Area of half a circle is, if you scoot up your notes, I think I'll stop scooping around, that's got to be distracting. But if you scooch up your notes, you can find that the area for half a circle is pi d squared over 8. So pi, I know what d is, I just solved for it, it's 369.47. That gets squared, put it over an 8, and let me work that out. And I'm getting, wow, 53607, 0.7, just carry another one for fun, millimeters squared. That's for the half circle part of this thing. What do you say we do the trapezoid now? That's not what I wanted to do. Go back there. There we go. Let's do the trapezoid part now. So, new color maybe. Come on, you. Okay. For the trapezoid, if you look back on your sheet to the trapezoid formula, it was basically, I think it went like this. A plus B over 2 times H. Formula looked like that, where you would use this as an A, you would use this as a B, and you would have to use this as a height. So the good news is I know what the A and the B are. A is the same as this diameter here, 369.47, plus, and B is the same as across the bottom there, 510. This has to multiply the height. Oh, we don't have the height. I want that distance there. Well, guess what? We're just going to have to go back over here to this triangle and now figure out the height, because the height of that triangle is going to be the same as the height of this whole thing. No beeps. Okay.
Here's what I found.
What? Siri's talking to me. You pain in the butt. Sorry. That's what I hate about keyboards. You touch a button, something happens. I hate that. Anyway, assuming I'm still recording, I believe I am. Let's figure out the height by using this triangle over here. Actually, I can just do this as a Pythag theorem, right? In fact, let me go to purple here. Pythag theorem. Let me insert this here. So separating this from this. Pythag. A squared plus the 245 squared is equal to the H squared. The A is down here, the 140.53 has to be squared, and then you would add the 240. Yeah, wait a minute. Gosh darn this thing. So you'll notice I'm screwing up again. Gotta stop doing this. Okay. A squared plus H squared equals 245 squared. That's better. You gotta make sure that you use the hypotenuse on the right. You have to use the hypotenuse on the right. So I caught myself. Good. That's good. I like catching myself. So getting back to what we were doing, H squared is going to be, take the 245 squared, subtract the A squared. But wait a minute, A is 140.53. So you got to subtract those two things. You got to take a square root when you're done. Let's see what I got here. 245 squared minus 140.53 squared equals, and then I take the square root of that, equals 245 squared minus 140.53 squared equals square root of the answer equals, finally, okay, so I got h equals, this height is 200.69. So that's what comes into this formula. And then over 2, let's go back to our old colors. So the area of the trapezoid is, punching buttons again, 369.47 plus 510 equals times 200.69 equals divided by 2 equals, it's a lot, it's 88,250, and I'll just give a decimal place, what the heck, 4.4 square millimeters. So we had 53,000 square millimeters for that, and this is 88,000 for this. I guess that makes sense. You expect the bottom to be rather bigger than the top. Anyway, the full area is going to be, to multiply these things together, what can I use for a color now? That one right there. So, area equals, add up the 88,000 to 250.4 and add up the 53,607.7. You end up with 141,858, wow, square millimeters. Now, here's a good spot to insert. Make sure you always answer the actual question. It said find the area. Yeah. It said in square inches. Oh, square inches. That's not square inches. Got to convert to square inches. So trig is one of the things you need to remember, and unit conversions is another thing you have to remember when you're playing around with all of these areas and volumes and stuff. So I'm going to have to do the old multiply by something to fix this trick. So you might remember, let's see, if you don't remember, look it up. But to get to an inch, basically 1 inch is the same as 25.4 millimeters, right? Except I have not millimeters, I have millimeters squared. I need to cancel millimeters not once, but twice. I need to cancel millimeters twice, which means that really, well, you can either say do this again, right? And now I'd be canceling millimeters twice. Or what you could do, which works just as well, is you could just kind of square this whole thing. In either case, we're going to end up with our square inches this way. So I take the number that's on my calculator, this 141,858, and I divide it by 25.4 squared. Whoa, that's not what I wanted to type in. 25.4 squared, and then I'll have square inches, and it's a much more reasonable number of square inches. I'm getting 219.88 square inches, which I like to carry 5 decimal places, or 5 sig figs, I should say. I like to carry 5 sig figs when I'm working these things out. When you get to the very end and it's time to circle an answer, don't worry about rounding back at that point. Oops. To 3 sig figs, or 4 sig figs if you want. Usually we carry 5 the whole time, and then we report like 3 or 4. So 220 square inches, that's the area of that thing. Whoa. Okay, so your homework's going to involve similar-ish stuff. You're going to need to remember your trig sometimes in order to figure out dimensions that you can put into the formulas. You're going to need to remember how to convert areas and so on. And like I was saying before, or in the other videos, down there you can also, if you had a question at any point during this lecture, you can just kind of note the timestamp and leave a comment. Question, really. leave a question in the comments, and I'll be able to answer it. I will be logging in. I'll make it a point to log in at least 4 times a week. So please feel free. It'd be cool to get some interaction going, get a nice little fact list, FAQ fact list.